Welcome to Blue Marble Geographics Ask the Experts. I'm Rachel Landry, and I'm joined today by my colleague Scott Weber, a quality assurance specialist here at the company. Today, Scott will be talking to us about NADCON5 and the US Geoid transformations in Geographic Calculator. All right, Scott, take it away.
Today we'll take a look at how to make use of two types of transformation products from the National Geodetic Survey, or NGS, that are implemented in Geographic Calculator. First, we'll look at the NADCON5 family of transformations, and then we'll do the same for the US Geoid models. What is NADCON5? It is an NGS tool, part of NCAT, and quoting NGS, NADCON 5.0 was a project to build and release transformation grids capable of performing three-dimensional coordinate transformations from a wide range of datums and regions in the National Spatial Reference System, unquote. What are US Geoid models? Again, quoting NGS, US Geoid models are, quote, models for transforming heights between ellipsoidal coordinates and physical height systems, unquote. Our sample data derives from a LiDAR dataset of the Augusta, Maine capital area with a coordinate reference system of NAD83 1986. That is the original realization of the North American datum of 1983. The LiDAR data is classified, and from the ground points, I created a digital terrain model, or DTM, in Global Mapper. Also in Global Mapper, I then digitized the Capitol Park boundary, applied elevations from the terrain model to the vertices of the boundary, and saved this vector feature as a shapefile with 3D geometry. We can see the terrain model and park boundary in the Geographic Calculator viewer. I've created 4 jobs in a project called NADCON5 and US Geoids. We have 2 interactive conversion jobs. These allow conversions such as projection changes or datum transformations of individual points. There is 1 vector conversion job where we will transform the 3D shapefile, but we could process the LiDAR data in a vector job as well. Finally, there is 1 raster transform job to show how we can transform the digital terrain model. I have pre-filled some information in all of these jobs to save us some time. In the first interactive job, we will convert the coordinate of the northwest corner of the Capitol Park boundary from NAD83 1986 to NAD83 2011. The source coordinate point is pre-filled with the name, the coordinate in degrees, minutes, seconds, and the source coordinate reference system is pre-selected as NAD83 1986. I will abbreviate coordinate reference system as CRS for the remainder of the demonstration. The target coordinate has only a coordinate point name. The entries are in red because they have yet to be calculated. Double-clicking the target coordinate reference system box, we can select the desired coordinate system. We can select from a list by choosing No here. Before I select the target CRS, each time I try to make a CRS or coordinate transform selection, the dialogues or pickers, as we call them, will pop up on my primary monitor, so please bear with me while I move each dialogue onto my secondary display for you to see. Navigating to Geodetic, North America, United States, I'll select NAD83 2011. Either entry will work in most cases, and the difference would be a topic for another discussion. Note that the CRS boxes each contain a date field for time-dependent transformations. We recently changed these from defaulting to today's date to being unset to require the user to think about what dates, if any, are appropriate for a particular transformation. NADCON5 is not time-dependent, so we can leave these unset. We will leave the vertical set to none to focus on NADCON5. To select the datum transformation, we double-click on the coordinate transformation box in the center. NADCON5 is the only transformation available in this case. And 2 notes on the NADCON5 entry. You can see that the accuracy field is blank. We have no method to report NADCON5 accuracy at this point, since accuracy is now computed on a cell-by-cell basis and therefore location-dependent within each transformation grid, as opposed to the earlier NADCON regional accuracy estimates. Also, since we don't know how many steps or grids will be used to get from the source CRS to the target, we don't know how the accuracy will compound in the final concatenated transformation. You will also see that there is no EPSG code for the NADCON5 entry. While EPSG has the coordinate operation method for NADCON5, EPSG does not have the individual transformations between any particular source and target. Selecting NADCON5, Calculator concatenates 4 transformations spanning 5 realizations of NAD83 and shows these in the transformation box. First, from 1986 to HARN. HARN is the High Accuracy Reference Network. Then from HARN to FBN, the Federal Base Network. Then from FBN to NSRS 2007. NSRS is the National Spatial Reference System. And finally from NSRS 2007 to 2011. Then we can calculate, and we'll see a small change in the target coordinate. And this change represents 18 centimeters. This means that if the data were 1986, but you assume they were 2011, you would be displaced 18 centimeters to the northwest. We'll see that later in a visual. In the second interactive job, in addition to NADCON5, we will complicate things by reprojecting the coordinate, adding a vertical coordinate system, and transforming the vertical coordinate. Again, the source information is pre-filled, but we have added a vertical coordinate from the terrain model and the vertical CRS NAVD88. The target coordinate has only a coordinate point name, and the target CRS is again set to NAD83 2011, but this time in projection UTM 19 north. We just need to add the vertical CRS NAVD88 by navigating to North America, United States, NAVD88 height. Again, we will select the NADCON5 transformation, but now we will see a Next button that allows us to select a vertical transformation if desired. Each US Geoid model has a source CRS of WGS84 ellipsoidal height and a target CRS of NAVD88. So in one calculation, we can transform from NAVD88 on one geoid model to NAVD88 on another geoid model via WGS84 ellipsoidal height by concatenating 2 of the geoid model transformations. As you can see by my point names, I'm going to transform from NAVD88 vertical from US Geoid 1999 on the source side to Geoid 2012B on the target. So I will select the generated transformation pair representing these 2 geoid models, NAVD88 to NAVD88 with WGS84 in the middle. Again, we see the 4 NADCON5 transformations, but now also the 2 geoid models. Then calculating, on the right, the target point is displayed in UTM 19 north, and the height is transformed between the 2 geoid models. The change in geoid models results in a 61.4 centimeter reduction in NAVD88 height. Also, since the output is projected, the UTM horizontal scale factor and convergence angle of the point coordinate are displayed. In the vector job, I have loaded the 3D shapefile of the park boundary. The CRS and transformation settings are similar to our previous job, except that the source file is UTM 19 north rather than geodetic NAD83. Again, we see the concatenated NADCON5 and US Geoid model transformations. I've set the output file to an appropriately named shapefile, and then we can process. Now in the viewer, we can see that 18 centimeter horizontal change due to the transformation as I described earlier. So this is zooming in on the northwest corner point. In the raster job, I have loaded the digital terrain model in the USGS DEM format. The CRS and transformation settings are exactly the same as in the previous vector job. I've also changed the output format from USGS DEM to GeoTIFF, which will result in a terrain model GeoTIFF since the input is a terrain model. I can process this job, and we can see it finish. Now, it would be difficult to see the small shifts involved on the terrain model, but you saw them for a point and for a vector feature. So there we have examples of NADCON5 and US Geoid model transformations of individual points, vector features, and a terrain model in Geographic Calculator.
Thank you so much for providing us with all that information. I do have a couple of questions for you if you have time.
Sure.
Great. My first question is when can we expect the next release of Geographic Calculator?
Well, we're expecting to release a service pack to the version 2020 later this year.
Can Global Mapper also take advantage of these transformations?
Well, if the user has both Global Mapper and Geographic Calculator, GeoCalc mode can be enabled to allow Global Mapper to access these transformations and many others supported in Geographic Calculator.
Okay, great. And what is the purpose of naming points in the interactive conversion jobs?
Well, interactive jobs can be recorded and saved in the form of a printable report, where the point names become very useful for distinguishing one report's points from another.
All right, and one last question for you, Scott. You
Okay.
mentioned time-dependent transformations. Can you tell us a little bit more about those?
Time-dependent transformations are becoming increasingly common, where the transformation applied is related to the collection time or epoch of the data to account for the ever-changing relationship between points on the surface of the Earth in relation to the geocenter of the planet. In fact, the NAD83 and NAVD88 datums of the NSRS will be replaced in or around 2025 with 4 new plate-specific horizontal reference frames and a new vertical datum. All data will need to include epochs so that new time-dependent transformations can be used. In fact, Blue Marble Geographics is already implementing tools to support these new reference frames in Geographic Calculator in preparation for their rollout.
Scott, thank you so much for joining us today. You are full of useful information, and we can't wait to have you back.
You're very welcome.
And thank you for joining us for this episode of Ask the Experts. And we hope to see you here next time.